Good morning. Today I'm going to tell you what is my plan for the workshop and ANSYS use. As you remember, we talked about fluctuating loads and fatigue, how important is a SEN diagram, and one of the very important items for the SEN diagram was this ideal endurance limit. If you have a SEN diagram, you can simply find this endurance limit for that material. If it's not available, you can approximate. And the ideal SEN diagram, ideal endurance limit is going to be multiplied by this correcting factor CA, CB, CC, CT, which are going to include the effect of environment, surface, loading, geometry, the effect of different contributing factor. And then we talked about mid-range stress and alternating stress, and I said those two stresses are very important to draw AM diagram for alternating and mid-range stresses. And to draw those and find those two stresses, you need to know what is maximum and minimum stresses. You can calculate maximum minimum stress using hand calculation or use ANSYS to find for a specific point what is the maximum and minimum stress, and then calculate mid-range and alternating stress. And using those two stresses, you can draw Goodman's line and finally find N, which is going to be a safety factor. If it's bigger than 1, you are going to have infinite life. If it's less than 1, the geometry you have designed is going to have finite life. Okay, now let's see what is my plan for the rest of workshop. We are going to have two types of loading. Okay, let me activate tablet noise. Okay, so this is going to be stress, time. And for the case 1, it is going to be zero-based cyclic mode. And the maximum stress is going to be 100 megapascal. The second type which we are going to work is going to be fully reversed. Fully reversed is something like this. And maximum stress is going to be 50 megapascal, and the minimum one is going to be negative 50 megapascal. Okay, you may ask, what is the geometry? Let me show you the geometry. Where is it? Geometry is going to be exactly the same geometry we had for the previous workshop. Remember, we divided and cut this geometry for smaller portion because we saw we have symmetry, and we can take advantage of that symmetry and have less expensive calculations. So this is going to be our geometry. Okay, so what we are looking for is safety factor and life and the number of cycles we can have for this design. First thing you need is you need to know what is maximum stress and minimum stress. So we can use ANSYS with static structural loading. For example, 100 megapascal, we can get maximum and minimum stress for the stress concentration area. And then use alternating stress formula and mid-range formula to find A and M, alternating and mid-range stresses. And again, using those two, we can find out our safety factor, which is going to be SE. I'm using Goodman's line formula, which we usually prefer, and SUT over 1 divided by n. If n was higher than 1, you can say we are going to have infinite life, and you remember when we say infinite life, it means 10 power 6 or 1 million cycle. If it's less than 1, finite life. And for this case, you need SE, and we said SE is going to be SE prime times some factors, correcting factors, which we are going to investigate that. For this workshop, the structure still is going to be our material. Let's see. Inside my tablet, I don't have ANSYS installed, but I took some pictures to show you how we can get some information which we need. For example, for yield stress, I selected structure still, and inside properties you can see yield stress is 250 megapascal. Let's write it down. So we found that SY for our material, which is a structure still, is 250 megapascal. What else we need? We need ultimate stress. Let me check where is ultimate stress. Again, inside the option, we have tensile ultimate stress, and it's 460 megapascal. Let's write it down. So ultimate stress is going to be 460 megapascal. What about SE prime, which is ideal endurance limit? Because it's still, you can consider half of ultimate stress, but I'm not going to consider and approximate this endurance limit, because ANSYS gives us a Venn diagram. If you go and select alternating stress, mean stress, you are going to have a Venn diagram here. And you can see it is extended up to 10 power 6 here, which is the maximum number we go and we consider as a infinite life. If you go up here to have 10 power 6 or 1 million cycle, the stress or endurance limit is 86.2 megapascal. So let's write it down. SE prime is going to be 86.2 megapascal. Okay, what else we need? Okay, we're done with this part. So we know ultimate stress, we know endurance limit. By the way, for this case, let's consider this correcting factor all 1. Later I'm going to show you how you can change it. So we have ultimate stress, endurance stress. Now you need to know what is alternating stress and mid-range stress to be able to find N. To find these alternating and mid-range stress, we need to go back to the ANSYS and calculate maximum and minimum stress there. Okay, let's go to ANSYS. Okay, now we are back in ANSYS. Let me first check the structural, the material we have for this static structure. It is structure still, and as you can see, alternating stress, we have a Venn diagram here, and for 10 power 6 cycle, it's 8.62 times 10 power 7 Pascal. Yield stress is here and ultimate stress is there. Okay, let's go back to the project and open model. I already opened it to not spend any time. Okay, let me suppress the force because we decided to use pressure at the left side, and it is going to be 100 megapascal. By the way, remember the supports we had? Let's check it. For this side, B, it's a frictionless support, C, another frictionless support, and for the button, we had one more frictionless support. Let me add pressure, and pressure should be applied to this surface. Apply the surface, and we said it is going to be 100 megapascal. Let's make it positive. Okay. Let's solve it. I didn't check mesh quality, so I need to go back for the mesh and check if it was default mesh or I already improved it. Okay, it's default mesh. So let's improve the stress concentration area. Let's see where is the maximum stress. So it is here. Oh, it's pretty good. No. So we have very good stress there, and let me make a note. The maximum stress is 435 megapascal. Okay, and it's going to be about this point. Okay, so remember and make a note this maximum stress. Minimum stress, it's 0. Let's consider this 0. It's a very small number. We are going to consider 0. If I want to find alternative and mid-range stress for these two values, let me drag this, because I know that sigma A is sigma max minus sigma mean. So it is going to be 435 divided by 2, which is going to be 217 megapascal. Great. So I know alternating stress. What about mid-range stress? It is going to be exactly the same because it is the formula for this is maximum stress plus minimum stress divided by 2. Minimum stress is 0, maximum stress is 435, so it is going to be exactly the same, 217 megapascal. So I have alternating stress and mid-range stress. Now I need to put inside Goodman line formula. Remember, it was sigma A divided by SE plus sigma M divided by ultimate stress, which is going to be equal 1 over n. Let's put these numbers inside it is 217 divided by 86.2 plus again 217 divided by what was the ultimate stress? Let me check. 460 is going to be equal 1 over n. Therefore, n is going to be 0.33. Three, 4. So this n is less than 1. So our design is going to fail under 1 million cycle, and we are going to consider this object have a finite life, and safety factor is 0.3, which we don't like it. Okay, let's consider case 2, which was fully reversed one. We calculate everything for zero based. That is why I added 100 megapascal. Now I want to calculate for fully reversed cycling, and it was 50 megapascal force, positive and negative, but I need just one side. So let's solve and find the maximum and minimum stress at the point we are interested. Let's wait for the ANSYS to calculate our maximum minimum stress and see. Let me divide this one. This one was for zero base, and I'm going to add fully reversed one. Let's check the stress. This time stress is 217 and the minimum is 0. Not because this is fully reversed stress, I applied positive force, which is toward inside once. The other case is going to be negative 50, so I need to calculate stress for the other direction. So for the positive 50 megapascal, the stress was 250. Let me write it down here before forgetting. So for case 2, sigma max is 217 megapascal. Let's find minimum stress. To find minimum stress, I need to change the direction of pressure and solve it. Okay, done. Wow, the maximum stress is exactly 217. But I changed the pressure direction. It should be negative. This problem is because I'm using equivalent stress. So equivalent is going to show me always the positive number. So let's check normal stress. And now Where is it? This is going to be positive, so let me check with the other one. So as you can see, I made a mistake for the previous one because I checked equivalent stress, not normal stress. And equivalent stress always show me the positive number. That is why I'm using normal stress this time to know what is the direction, which do I have positive or negative stress. Yeah, so the first one was negative 217 and the second one was positive 217. Let's write it down. So maximum stress was 270 megapascal and minimum stress is negative 217 megapascal. Okay, which makes sense because we need, this is fully reversed, and the graph was something like this. So we should have positive, negative all the time. Let's find life as we use the Goodman's line. For this case, let me find alternating stress, which is going to be this one minus this one, which is going to be twice that, divided by 2, so 217 megapascal. What about mean stress, mid-range stress? It is going to be summation of those two divided by 2, so 0. Done. Now let's use Goodman's line formula. Alternating stress is 217 divided by endurance limit 86.2 plus this one is 0 and 460. Okay, is going to be equal 1 over n, and n based on this calculation is going to be 0.397. Okay, so this is, the blue one is fully reversed, the black one is zero based one. Okay, now we are going to calculate using ANSYS, because ANSYS can do it much easier than this hand calculation, and for all points. This hand calculation was just for 1 point. Okay, let's go for case 1. Case 1 was 100 megapascal, 100. Okay, let's solve it. Come on. Because quality of mesh is very good, it takes a bit of time. But if I were you, I would improve the quality of mesh just for the tip of the stress concentration area using like a sphere mesh area to have the local mesh improvement. Right click over solution, go inside insert, for fatigue select fatigue tools. Okay, let's see what we have here inside this option for fatigue. First one is fatigue strength factor. This is exactly the correcting factor combined. So you have CA, CB, CC, CD, each applying the contribution of different factors. You can multiply all those factors to each other and apply that the final number here, which could be 0.9, 0.8, 0.3, anything else. Okay. Type of loading, let's see how many options we have. We have zero base, fully reverse, and ratio and history data. For the first case, it was zero base, so I'm going to select zero base. As you can see here inside this graph, our stress, the minimum stress is going to be 0, and the maximum is 100 megapascal, which we want. Scale factor. Scale factor, this one, is going to help us if you want to do parametric studies. For example, for this case, we have 100 megapascal. Next time you want to make it 200, 300, 400. You can click over this box, make it parameter, and then use for parametric studies. The next important option is analysis type. We have two options, stress life and strain life. Strain life is usually used for low cycle calculation, and stress life is for high cycle fatigue calculation. So because we usually work with high cycle, we are going to select stress life. The next one would be mean stress theory. As you can see, the first one is Goodman, Soderberg, Gerber, mean stress curves. We have different cases, and we can select these. These are the decision making tools for engineers. Depends on your understanding, or for the industry you are working, sometimes we can select different types of theories. By selecting each of these theories, you are going to see on the right side the graph for that case. For example, for Goodman, the green one is for Goodman. If you select Soderberg, it is going to be the red one. We are going to use Goodman as I explained earlier. And all the calculation is going to be based on equivalent stress and nothing more important. Okay, now let's add a few results. Inside counter results, you can add life, damage, safety factor, and by axiality indication. Good. Let's solve it. As I told you, this solution must be much faster than the initial solution because fatigue calculation is post-processing calculation. It just uses all the information available here to calculate the rest. Okay, let's see. Let's start with the last one. This one shows that what type of loading we have there. If it's the number is close to -1, we have pure shear inside. As you can see, we have a blue area which we have pure shear. If the number is close to 0, like this area, this green area, we have pure one directional loading. So the orange, yellow would be just one directional loading, which is the majority of our structure or geometry. And then if the number is close to 1, we are going to have more bidirectional, or load is going to apply at two directions. We have this red and this red area, which we have loads at two directions. It's good information, but not that much useful. What else? Let's check life. As you can see, we have lower life close to stress concentration, and blue area is the infinite life, which we say 10 power 6. As you can see, ANSYS also consider 10 power 6, and this area is going to have less life. Let's see safety factor. For case 1, which is what was the zero-based load, it's 0.33. Let me see what we found. Oh, it's pretty close. Our hand calculation shows here the safety factor 0.334, here 0.3338, which is almost close to 4. So for the red area, we have lower safety factor, less than 1, which is going to tolerate 2,458 cycle, as you can see here. What else we can see? For this area, we have about safety factor of 5, for the green area 10, and if we had blue area, those areas are going to have maximum of safety factor of 15. Usually ANSYS won't go above 15. Let's see damage. For the damage, if the number is close to the 1,000, we're not going to have any damage. As that number increases, the possibility of the damage increases. It's kind of not bad information about the possibility of damage, but we usually prefer safety factor and life, which is the quantitative numbers we can investigate. Let's add one more information: fatigue sensitivity. Oh, it's interesting. We have, your friends are sending their workshops here. Okay, we have loading history and life cycle. This graph is very important for us because number 1 is our current load. So our current load, the life is going to be about here. I don't know what is the number, but it's less than 10 power 6, so much smaller number. And it is finite life, and we don't like this type of design. So you need to decrease the load, and if you decrease our load up to 50%, our life is going to increase up to 89,000 cycle. Let's check that one. I'm going to decrease our pressure to 50% smaller number. So 50. Let's solve it and check how fatigue sensitivity is going to change. Okay, I decreased my load, my pressure 50% smaller, and reached to this point, new point, and as we expected, our life cycle increased a lot. But still, our design is not for the case of infinite life. If you want to have infinite life, you need to decrease your pressure up to this level to reach 10 power 6. Let's see. From 0.5 to 0.7, we have 1, 2, 3, 4, 5, 6 sections. Okay, let me see how much I should decrease my load to reach this point. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this says 0.5 divided by 12 sections, and I need to decrease 6 times or 7 times. Let me count once more. 1, 2, 3, 4, 5, 6, 7, 8 times 8. So I need to decrease 0.33 times. So this one times 50, it is going to 16.66. So let's decrease pressure to 16.6 megapascal and check the fatigue and its sensitivity. As you can see, ANSYS can help me a lot to select better load for my design. If I don't want to change the load, I need to change the geometry, because this geometry can't tolerate high number of cycle, which we usually prefer 1 million cycle to have like infinite life. So let's see. Yes. Now we can see, oh, I think I made a mistake. It's too much. So let's multiply by 2. Multiply by 2, 33.33. I made a mistake, I think. So you need to always be careful not to make a mistake. Let's see. Yeah, I made a mistake there. Because that sections was just for half of the, from half to 1. I can say for the 0 to 1. Yeah. So as you can see, currently, my current load is going to have infinite life, and my current load is this pressure, 33.3. If I decrease my the number of cycles won't change. I already reached to the infinite life. If I increase it to 1.25% of the current, the life is going to dramatically decrease. So using this fatigue sensitivity, you can easily calculate and find which load is proper load to have infinite life. Okay, so we did this calculation for the case of zero base load. Let's go for the case 2, which was 50 megapascal, and fatigue was fully reversed. Let's check. I don't remember what we calculate here. Let me check. Okay, we found for the fully reversed 1.39 safety factor. Okay, let's check safety factor. 0.396, 0.397, very close. So our hand calculation proves we did a good job, and the approximation is pretty good. So this fully reverse loading has a little bit higher safety factor than zero-based one, which is interesting. Think about it, why we have better life or safety factor for fully reversed than zero-based. Okay, let's see other things. Life, we have 18,000 life as a minimum life for this stress concentration area, and blue would be the infinite life. Nothing is going to change for this directional identifying directions of the loadings. It's a little bit difficult for me to pronounce this. And let's see our fatigue sensitivity. Again, we're not reaching to the infinite life, 10 power 6. Let's decrease 50%. I'm going to decrease 50%, so 25. Okay, now we can see our current position. We increase the number of life cycle, but we haven't reached still to 10 power 6. We need to decrease our load to reach this number. 1, 2, 3, 4, 5, 6, 7. Okay. 8, 1, 2, 3, 4, 5, 5 and 7. Okay, how much I should decrease? Let me if I decrease 25%, I'm going to come to this one. Let's go for that one. So currently it's 25 megapascal, and I want to decrease it 25%, so 75, 18.75. Let's go with that one. I didn't calculate exact point we can reach 10 power 6. For your calculation and workshop, you need to do the exact calculation. Okay, it's almost ready. Yep, see, I went 25%, but I didn't need actually. I could increase the pressure a little bit more. You need to find the exact pressure point here. So we reach to the infinite life, and our design is very safe right now for fully reversed one. Okay, now I want to consider correction factors. Remember what was the correction factor? Let me write it down here. Correction factors was when we want to calculate SE or endurance limit, you multiply ideal endurance limit SE prime by some coefficient CA, CB, CC, CD, CE, CF, a lot more. And I said ANSYS won't accept these coefficients one by one, but it can accept the combination of those coefficients. So let's consider this combination of these coefficients 0.3. So let's go here and add 0.3 there. If I add 0.3 there, my SE or endurance limit is going to be 86.2 times that 0.3, which is going to be 25.86 megapascal. Okay, let's do the calculation using the new SE. Okay, so I'm going to change this 86.2 to new endurance limit, which we just calculated, 25.86, and this safety factor should change, and it is going to be 0.112. Let's do the same for the fully reversed loading. So let me add this value here, which is going to be 25.86, and the value for fully reversed cyclic loading is going to be the safety factor is going to be, I think, 119, sorry. Again, for the fully reversed loading, safety factor is again a bit larger. Okay, now let's go and check it. For the first case, we had 100 megapascal, and it was zero based. Let's solve it. safety factor. 112 for case 1. Case 1, 112. Pretty good. Let's go for case 2. It was just 50 megapascal, but fully reversed. Let's go and calculate that one. Okay, where is safety factor? 119 almost, and our calculation showed 119 for fully reversed one. Okay, so the important thing we learned, it is really important to consider fatigue for the case you have cycling loading. If you have a cycling loading and your design is outside and it deals with environment, temperature, wind, different level of the surface, different types of loading, you need to consider correction factor, because correction factors directly can have effect on endurance limit, and they are decreasing that endurance limit. And as you can see, for this case it is 119 the safety factor, but it used to be 0.3, so 3 times smaller because environment effect. So remember to consider those case too. Okay, thank you very much. Now it's your turn to start do the workshop.